Hi, this is the first presentation addressing Chapter 1 of the book entitled Fundamentals of Quantitative Design and Analysis. After watching this presentation and completing the learning task proposed at the end, you should have achieved these specific learning outcomes addressing the evolution of computing performance, the computing and parallelism classes, and instruction set architectures. Let me start by explaining that each slide contains an indication of the page numbers that you can read to find additional information. And I'm referring, of course, to the 6th edition of Hennessy and Patterson's computer architecture book. It is remarkable that processor performance improved by 50,000 folds in the 50,000 times in the last 40 years. And this improvement in performance, however, was not linear over this period, as we will see, and started to decline in the beginning of the current century, leading Intel to focus on multiprocessor architectures. Mostly for technological reasons, the processor performance is now doubling only every 20 years. Now, this graph shows the 20,000-fold improvement that was referred in the previous slide. It shows that processor performance doubled every 2 years for nearly 2 decades. But then it steadily started to decline since 2003, in this first case due to power limitations and also to architectural limitations of uniprocessor architectures. Well, multiprocessor architectures and other forms of parallelism became the dominant paradigm after 2003, but their own limitations caused another decline in the rate of performance improvement in 2011. And then the end of Moore's law in 2015 brought us to the current 3.5% improvement rate per year. You may check the detailed caption that accompanies this graph in the book for further information. Now, this table shows that the application domain determines the various classes of computers as we know them today. Real-time media performance, for example, and responsiveness are important features for processors used in personal mobile devices. On the other hand, warehouse-scale computers are designed so that tens of thousands of servers can act together as one. The Google Translate service that lets you use your cell phone camera to translate in real time a sign written in any of the 90 languages supported is one example that runs in a warehouse-scale computer. And of course, throughput is a key feature in this case, since many thousands of people may be using this service at any given time. As a final example, the processors used in Internet of Things or IoT devices are selected because of their application-specific performance. Well, in pages 7 to 10, you will find additional interesting information with this respect. I said a while ago that Intel changed its focus from uniprocessor to multiprocessor cores in 2004, but there are various forms of parallelism, and some of them were already being used in uniprocessor architectures. The book considers that parallelism in applications takes either the form of data-level parallelism, where many items of data are operated on at the same time, or task-level parallelism, since many of the tasks involved by a given application can operate independently. Now, computer hardware can exploit these two forms of parallelism in multiple ways, as shown here. Instruction-level parallelism, or ILP, is probably the oldest form and was already in use with uniprocessor architectures through pipelining. The second way exploits data level parallelism, while the third uses either data level or task level parallelism. And last but not least, request level parallelism addresses the case of largely decoupled tasks. So there's a broad classification of parallel computing classes that was already developed by Michael Flynn more than half a century ago, but which is still in use today. These classes consider the four possible combinations between single or multiple instruction streams and single or multiple data streams. Single instruction and single data, or SISD, is the standard sequential computer case where instruction pipeline represents a form of instruction level parallelism. Well, I invite you to elaborate further on the other classes and then to check what is said in page 11 of the book with this respect. Notice that warehouse scale computers belong to the fourth class, since they are a loosely coupled MIMD architecture. The background that we have addressed so far should make it clear to you that the architecture of a computer goes far beyond the design of its instruction set. The instruction set architecture nonetheless continues to represent a key factor in computer design, and indeed it serves as the boundary between software and hardware. An instruction set architecture comprises the 7 dimensions shown in this slide. You are certainly already familiar with at least some of them, such as operations and control flow modes. But I think that the best way to realize their importance is to read the descriptions that are presented in pages 12 to 14 of our book. What follows from here is a case study addressing the RISC-V, or Reduced Instruction Set computer, instruction set that was developed at the University of Berkeley in California. And I'd like to recommend that you take the time to read through the registers, instructions, and instruction formats that are described in pages 12 to 16 of the book. So thanks for your attention.